G'day viewers. In this segment I'll talk about securing the web. Wow, well securing the web is actually a very big topic. What I'm really going to do, since we're talking about network security here, is focus on the protocols called SSL and TLS, which are used as part of HTTPS, which I bet you've heard of since you no doubt enter many HTTPS URLs or see them in your browser. And I'll also talk about something called certificates as part of this. They're a key part of the operation. Okay, so goal and threat model. Let's start off again. This is particularly important here because, well, I think you know many things can go wrong on the web today. Clients can run into all sorts of malicious content as they surf around the web and download strange web pages. Web servers are often the target of break-ins by external parties, compromising different bugs on the servers to gain control of it and see what data is on it. There's all sorts of phishing scams with fake data misdirecting you in other places in different ways to steal your data and so forth and so on. The web is a bit of a dangerous place just to be out there. What we're going to focus on, however, is a much more restricted subset of the general web security problem. Our goal really is to secure HTTP using a protocol called HTTPS. That stands for HTTP Secure, if you like. Now, by secure HTTPS, I mean that we should defend against several attacks, and they're listed here. And you can see that these are all attacks or threats that are focused on the network portion of the protocol. The first attack is against eavesdropping on traffic between the client and the server. So someone being able to read the messages that you send between a client and a server as you use HTTPS, as you download that web page or post and upload your mail. The second threat is tampering with this traffic as it goes between the client and the server. Maybe that's changing your mail message as it's sent up from the client to the server. So it looks like you sent a message that's different than the one you actually did. And the third threat is that of impersonating a web server. When a client's talking to a web server, it thinks it's talking to a certain server. It should be right. So if you think you're talking to your bank, we would like it to be the case that you really are talking to your bank, or at least that you have some way to check that. You'll notice that all of these threats relate to the network portion of the protocol here. So what we haven't done is focused on break-ins to either the client or the server, or malicious content which is downloaded by them and exploits bugs in their operating system and so forth. That's a great topic, it's just wide of what we're looking at. So HTTPS, that's where we're heading. What can I tell you about HTTPS? Just to give you a little bit of context first. Well, HTTPS is actually an add-on to HTTP. What it really means is simply running HTTP over these other protocols, SSL or TLS. SSL stands for the Secure Socket Layer, and TLS stands for Transport Layer Security. SSL was the protocol that came first. It started as a proprietary version, and eventually it was standardized under the name TLS. So TLS is the more modern version of it. But now this protocol is really inserted here, that's what I mean, it's an add-on, between HTTP and TCP. So HTTP is running unaltered, it's now running over a transport which encrypts everything and provides some kind of security. TCP is also unaltered. TCP is just moving information around. It doesn't know that the information is encrypted. And the approach by doing this is that one could reuse all of these components without altering them, yet add important security properties to the web that protects against some of the most common threats that we worry about. A little more context just in terms of the timeline for how all of this evolved. SSL was actually a protocol pioneered by the company Netscape. Starting in the early 90s, I think, SSL first came out publicly as SSL version 2, which had cryptographic flaws in it, and it was fairly soon fixed into SSL 3, which is the more standard version of SSL that you should see around today. That's been standardized since and available since 1996, so it's really been out there for some time. It's maybe the most common version of SSL and TLS that's used today, perhaps. TLS is an IETF standard, so it's not a proprietary protocol. TLS has been standardized since '99, and it's been revised slowly in the years after that. TLS is still a protocol which is being deployed today in the internet to provide security, both for HTTPS and actually, you might notice the name here is Transport Layer Security for TLS. It's not specific to the web. So increasingly you'll see things like email with the SMTP protocol sent over TLS. So it can really secure any kind of transport application. That was the intent, that it be used more widely. Actually, the motivation for all of this was really web commerce. So people buying things over the web and typing in their credit card number and sending it from the client to the server. They wanted to make sure that this information would be sent securely and so that no one else on the network could steal your credit card number. This was the genesis of HTTPS. The adoption was actually rather slow. Initially it was just used for credit cards rather than everywhere. Partly due to the difficulties of just rolling out any change, partly due to the performance hit that it took to do some of the public key cryptography in HTTPS. Today, that's a little less of a concern, and HTTPS is being rolled out really everywhere. It's now in widespread use, and it can be used by any app, not just HTTP. Actually, apps and HTTP are all being blended together. So your email application running in your browser is a good example. There is a lot of traffic on top of HTTP. An application on top of HTTP is implementing this email. It's likely to use HTTPS as a transport so that all of your mail will be sent around securely. Actually, if you look at systems like Gmail, which ran in your web browser on top of HTTP, when they first came out, they didn't have security. They didn't have HTTPS, so your email was being sent in the clear. It's a while ago now, but at some point, due to people realizing what was going on, there was increased pressure to use HTTPS to move your mail around while encrypting it, so not just anyone could read it. Now it's standard that your mail application in your browser and many other applications will use HTTPS by default. And I would expect it to be more of a default over time, not less. So we'll switch now to SSL because HTTPS was really HTTP over SSL or TLS as the standard version. So we just want to know what SSL or TLS does. So in terms of operation, the protocol is really providing a couple of features here. It's allowing the client to verify the identity of the server to make sure that the client's talking to the right web server, someone who really is your bank, not just pretending to be your bank. Optionally, it lets the client identify the server, but this is typically not done in the web usage. It might be useful in other protocols like your email exchange. And as well as verification, we would like to provide a secure message exchange between the two parties. So after they've identified one another and everything's good, they should be able to send encrypted messages that give all of the usual properties of confidentiality, integrity, authenticity, and freshness. And to do all of this, we really have an authentication phase where the client's working out who the server is, making sure they're really who it thinks it is. As a side effect of this, we're going to end up setting up all of those session keys, which we can then use for encryption. And the encryption is all used as part of the data transfer phase to make sure all of the messages are secured. Well, all of the magic then for us is really in the authentication phase. Afterwards, we're just using standard kinds of encryption for confidentiality, integrity, and authenticity. Boy, I'm getting a little sick of saying that. You're probably getting used to those phrases for that being a secure message exchanges. So let's just focus on the authentication. The whole point of the authentication here is to allow the clients to securely connect to servers that they haven't used before. If clients were always talking to just a few servers that they knew and trusted, we could set up keys between them and everything would be great. But in the web, you're always talking to some party, it seems, that you've never met before and you want to exchange information securely with them. So the client's going to need to authenticate that the server is who it says it is. And this, when it's used in your browser, by the way, we also want to reflect security properties to users. You'll often see in a browser some it used to be a lock on a page or other visual indication that the page has been authenticated. So you really knew who it came from as well as it was sent securely. And as I said, the server typically doesn't identify the client, at least in web usage, because any client can use a server. It's not just that anyone can buy anything, it's usually that the identification of the client as part of credentials like a credit card and so forth is done later. It's not used as part of the SSL exchange. Now, for the client to identify the server, especially servers we haven't seen before, we're going to end up using public key authentication. That way servers can just publish their key, and if clients can get it, then they can authenticate the server. But we still haven't answered really how the client gets that server key. Where does he go to look for it? The server's web page or what? Well, to solve this problem, we'll end up using something called certificates. Certificates are messages which really serve to distribute public keys and other information. A certificate binds an identity to a public key. So here's an identity, Robert John Smith, and an email and whatever, and here is a public key that corresponds to the identity of Robert John Smith. This certificate is binding these two together. The identity here is a name and an email address for a mail certificate, but in the context of a web, what you would probably have here is a domain name, like so that your bank is bound to a particular public key. This certificate, it just says what these two things are, but it then needs to be signed by someone you trust, again using public key cryptography. And we'll get to this in just a minute. This is the whole crux of it. And these certificates are commonly put together in a format called X509. You might hear or see that around. But the certificate is really used to distribute these public key bindings, as long as we can just verify the signature bit. So let's get to that next. Okay. So these certificates, just to get towards this validation question, these certificates are what is part of what is called a PKI, a public key infrastructure. A public key infrastructure gives you everything you need to manage and distribute public keys for everyone. So it's going to use these certificates, and importantly, it's going to end up adding hierarchy to these certificates. So you can see here in this picture we have a hierarchy. We go from the root down a level and down another level. And the purpose of this hierarchy is to let many different parties issue these certificates. If there was just one server that issued certificates, everyone with a website in the world would have to get this one server to issue a certificate binding their identity to their public key. So they would have to go and show themselves to this server and all of that. Instead, we would like many different parties to be able to issue these certificates. These parties are called CAs, or certificate authorities. So there might be different companies running in different countries and so forth. This will sort of remove that bottleneck and let many people, by letting many people issue these certificates. Of course, we still need to be able to verify that these certificates are good. Here we have a situation where a particular certification authority, CA1, is certifying the ABC website. So this message CA1 would be sending a message which says, for the ABC website, this is the public key. Suppose we get that, we would like to know if that's actually correct, because we don't yet know CA1. So the question really is here, how we can verify the information that we receive in a certificate. So say you're a web browser, and you want to contact a particular website, the ABC website, and you receive from CA1 this information about the ABC website that tells you it's public key. Great, you know the public key, except you haven't yet verified that it's correct, and you want to do that to make sure you're talking to the right party. So how does the browser do this? Well, Well, in your browser, we have to start somewhere. So you have, as a trust anchor, a root of trust. Your browser is programmed with the public key of the root of this hierarchy for the PKI. It just has it and it assumes it is correct. The root can then tell you information about this other box here, RA1. This is an intermediate authority who's issuing certificates. So in fact, the root can make a statement to say that RA1's key is X, some key X, and sign it using its key. Now you can check this because you have the root's public key, so you can check that this statement has been certified by the root, in which case, if you trust the root, you will believe that RA1's key is X. RA1 can then make a statement saying that CA1's key is Y and sign it by its with its own key, and that would be X. So it would be signed by RA1 with X, and this would be right. Let me just put that notation in to make the linkage clearer in this figure. So you'll then be able to, since you have the key X, you'll be able to verify whether the statement is true, and you will learn the key for CA1 is Y. Now you're able to take this statement that you got from CA1 saying that ABC's key is some other thing Z, which is this is the bit you want, and you'll be able to check the signature from CA1 using the key Y to see if everything matches. If it does match, then you will have the public key for website ABC, and you'll be able to use it as part of the SSL exchange to see if you're really talking to ABC. Let's see how that works next. Oh, before we do that, just here's a picture in more browser-specific terms. So I said what your browser did in terms of having the public keys of the routes and so forth. But you can look at this yourself. So your browser or your operating system has inside it, is configured when you get it with the public keys of what are called the trusted roots of the PKIs, these at the very top of the tree. These are called, it has things called root certificates. So it's a certificate that's signed by the root itself that you just sort of take to be true, that tells you the root's public keys. Now, it's interesting here, if you look inside your browser, you might find there's not one root certificate, but many that your browser trusts. Maybe there are 100 different root certificates that are out there and trusted by all of the different browsers. This is actually a problem because it means that in deciding whether you are talking to the right website, your browser is trusting maybe 100 different parties. The more parties you're trusting, the more risk there is that you're actually going to end up trusting someone who shouldn't be trusted. So it's a little problematic that you're depending on so many people and you may not even realize who you're depending on. If you'd like to see some of this, you can use your browser itself. Just under some of its options, there will be a place to inspect the certificates, and you can have a look yourself. And you'll see all of this information inside your browser so that you can inspect it and configure it and override it if you want. On the right here, I've shown the certificate for wikipedia.org, and as you would find inside a web browser. And so you can see a few details here. You might not be able to read that. But it says it's issued to wikipedia.org. It's a certificate that it tells you the all of the details here would have the information about the public key for wikipedia.org, and you can see that it's been issued by some certificate authority here, DigiCert. And there's various fingerprint and signature information that you can use to verify everything's good. Okay, I still have a little more to say about PKI as it turns out. This is a detail that I don't want to go into, but I just do want to tell you another real-world complication. So this should really give you a sense that working with public keys is not straightforward just because they can be public. There are a few wrinkles involved. Here, another real-world complication that public key infrastructures need to deal with is this one. Public keys can be compromised. Your computer could be hacked into. Your computer was where you stored your private portion that corresponds to your public key. Someone has stolen it. Now they can sign things as you. So that key has been compromised. Well, to allow for this to happen, we need some way to revoke certificates which are signed by this key. Because now they can no longer be trusted, at least in the future. And so what a PKI includes, as well as all of the machinery to distribute these certificates, is something called a CRL, or a certificate revocation list. This is really a list of bad certificates which are no longer considered valid and they can no longer be trusted, even though they're within their expiry date. And it's really a way to weed out some of the bad keys there. So all PKIs will also need to provide a certificate revocation list. Okay, so now we're at the stage where the client has somehow got the public key for the web server that it wants to contact by using all of this PKI and verifying things all the way down the hierarchy. Wow, that's quite a lot of work actually. But now we get to go through SSL authentication. This is a timeline, so again time goes down the page here. This is a timeline for SSL version 3 authentication. And like, wow, this is complicated again. I'm not going to explain all of it to you. It's there so we can see it. There's more information available in your text and other resources to learn more about how these protocols work. I'll just sketch a few features of it for you. Now, first of all, some of the first steps here is a bit of a negotiation between the client and the server. Many different cryptographic algorithms can be used. And so the client usually tells the server what algorithms it speaks, and the server out of them chooses when it intersects what ones the client speaks and what ones it wants to use. It tells the server what algorithms they're going to use. You can also see, as part of the information that's going here, the server is helpfully sending back its certificate information and everything it needs so that the client can verify the public key of the server. Right? That's how, using only the trust anchors which are already in the browser and the server. So this is just a phase for everything to get initialized. And here is that Alice checking the certificate from Bob, that website, which could be ABC or some other website, using these certificates. Now this is all before we actually do any of the authentication. Now we want to do the authentication. So what happens? Well, Alice essentially computes some what's called a pre-master key that is sent. This is sort of keying information which Alice can compute using all of the information she has so far, including information about Bob's public key. The real Bob, and you can see here, it's encrypted with, it looks like it's encrypted with Bob's public key. The real Bob, if he possesses the right keys, will be able to understand these messages and also compute the session key that Alice has computed. So Alice now switches to the session key and Bob switches to the session key, and we're finished with this protocol. So if they, again, this is like 8211, if they can both compute the right session key, and they don't send it to one another directly, they just have to both compute it, then they can both switch over to use it, and if they can both understand it, and all of this is happening when we send the change cipher messages to know when to switch over. If they can both understand the new messages, then everything's good. Alice has successfully authenticated to Bob, and they've set up an encrypted session. And down here you can see the encrypted data messages just flow back and forth between the two now that we've set it up. And that's SSL version 3 authentication. And now we've seen how HTTPS works. I guess I'd like you to take away a couple of things from this. The main thing I'd like you to remember is just SSL and TLS is used with HTTP to make a secure transport, HTTPS for the web, and as well as SSL and TLS being available as a secure transport for other applications. We'll see more of this in the future. Secure here means all of the usual properties that we want, confidentiality, integrity, and authenticity, as well as the client being able to authenticate they're talking to the right web server. These protocols are very widely used today in the web, and they'll only be more widely used in the future. You can see here as part of the protocol, the client's authenticating to the web server. I guess I'd also like you to remember that this is done with a PKI and the use of certificates. And as you can also see, that some of this is quite complicated. Both the authentication and the certificates are major areas of complexity and hence risk. We sort of take all of this for granted because it's inside the protocol. If everything's used in the right way, it works fine. But it's worth understanding what's really going on so you know what you're actually depending on.